Floods can be devastating in terms of the loss of infrastructure and assets, but the real tragedy often lies in the lack of time that emergency managers have to warn people about what may be coming their way. The critical minutes or hours between when a heavy rainfall is forecast and when the flood waters actually reach a home. For many decades, we have been relying on static data and models to understand which areas would flood. It could take hours to prepare the data for analysis and run the models, which meant that if a storm were to hit suddenly, or if the rainfall was heavier than expected, there was not sufficient time to adjust the predictions and update the warning systems. Digital twins are changing how we predict flooding and, in turn, how we warn people about the imminent risks. A digital twin is more than a 3D map. It is a live virtual replica of a physical system. Digital twins are a revolutionary tool that are transforming our ability to manage the world's most costly natural disaster. Digital twins allow us to ask questions in different ways. For instance, instead of asking what might happen if we get 10 inches of rain at some point in the future, a digital twin allows us to ask a more specific question like what is happening right now and what is going to happen in the next 30 minutes if the storm intensifies. Simulations are the engine of a digital twin. Simulations allow the twin to move beyond real-time monitoring to predict, analyze, and optimize physical assets and processes by running what-if scenarios. These what-if scenarios can provide insights for proactive decision-making, risk mitigation, and operational efficiency. A digital twin for flood simulation has three critical components that link the physical world to the virtual one. First, a detailed three-dimensional representation of the real world is needed. This digital surface model is usually built from LiDAR, radar, or drone-based surveys and includes the terrain, surface features like buildings, roads, and bridges. And if available, it also includes the stormwater infrastructure like drainage pipes, pump stations, and storm sewers that are usually located underground. The more physical detail the digital surface model can capture, the better the predictions will be. The second component is the real-time data that turn a static model into a twin. These real-time data might come from devices in storm drains that measure water depth, flow velocity, and blockage status. They can also include real-time data on precipitation, soil moisture, and river levels from weather stations or satellites. At an operations level, real-time data might also include sensors that monitor whether a pump station is running or a floodgate is open. The third component of a digital twin for flood simulation is the hydrodynamic engine. This is the brain of the twin. It's a sophisticated 2D or 3D hydrodynamic model that constantly runs within the twin. It takes the real-time data, processes it, and simulates the physics of water movement, not just in a river channel, but across the streets and floodplains of the landscape. Now, the power of the digital twin lies in its ability to facilitate two core functions, planning and prediction. Because the twin is a perfect copy of the system, urban planners can use it to test infrastructure projects without ever digging a channel or replacing a culvert. For example, a city planner could use the digital twin to simulate building a new subway tunnel and test how that might affect stormwater runoff. Similarly, the planner could simulate whether upgrading a bridge might create a dangerous bottleneck for floodwaters. Engineers can run simulations based on extreme future scenarios, such as the occurrence of a 1 in 500-year flood event, combined with a 1-meter sea level rise, to see if current defenses like seawalls or retention ponds are adequate, allowing for targeted, optimized investments. Beyond planning, a digital twin can facilitate real-time predictions and responses that can move disaster management from reactive to proactive. For example, by integrating real-time rainfall forecasts, the twin can quickly run a simulation and predict exactly which streets or areas will be inundated and exactly how long before the water gets there, providing early warning to those affected. If a flood starts, emergency managers can see which roads are submerged, simulate the fastest viable evacuation routes given the real-time road closures, and decide where and when to deploy flood barriers or pump equipment. For urban areas where stormwater drainage management systems must carry away excess flow, a digital twin can monitor how full the storm sewers are getting or whether there are blockages preventing flow. Digital twins are driving a major leap in flood management. More than just a map, they are risk assessment tools that marry artificial intelligence with real-time sensors and high-resolution modeling to advance planning and prediction, ultimately saving time, money, and even lives. Digital twins are shifting the future of flood analyses from static models to continuous predictive intelligence.